Hi everyone, I'm Muhammad Yousaf, the corresponding author of this manuscript. Manuscript ID is 2020 PSPC 1003, and the manuscript title is A Control Strategy to Mitigate the Sensitive Deterioration of Overcurrent Protection in Distribution Network with Higher Concentration of Synchronous and Inverter-based DG units, authored by Muhammad Yousaf, Kashem, Muttaqi, and Sutanto from University of Wollongong, Australia. A large-scale integration of synchronous and inverter-based DG units has improved the power quality and reliability of the electrical networks, but they have introduced a lot of protection challenges that including the sensitive deterioration or the protection blindness of the overcurrent protection devices. So in this research work, we have investigated the impact of DG penetration level, the impact of fault impedance and DG and fault location on the sense deterioration of the overcurrent protection devices. So in the absence of DG, for a fault at point F, the fault current passing through this main breaker IFCB is computed by this mathematical expression. So if when we integrate a DG at bus B, so the fault current sensed by this breaker for the similar fault condition is reduced, as can be seen in this mathematical model. So this reduction in the fault current sensed by the overcurrent protection devices may delay the tripping of the overcurrent protected devices, causing the nuisance tripping of the protection network. What are the network parameters that affect the sensitive deterioration of the overcurrent protection devices? So for IEEE 13 node test feeder, it can be seen as the DG penetration level increases, the sensitive deterioration or the protection blindness of the overcurrent protection devices goes on increasing. So for the fault location away from the grid side, so we can see the sense deterioration is experienced at its peak. And we can also see as the fault impedance increases, the fault current seen by the main breaker goes on decreasing, and the percentage of sensitive deterioration goes on increasing. So it means like the increasing DG penetration level or the increasing fault impedance will greatly affect the sensitive deterioration of the overcurrent protection devices. So this issue has not been addressed in the previous studies. So what are the impact of the DG location on the sensitive deterioration? So we can see when the DG location is near to the grid, the sensitive deterioration or the delay in the tripping of the overcurrent protection devices seems to be more worse. So it can be seen when the DG location is at node 633 for IEEE 13 node test system. So after about 50% of DG penetration level, the tripping of the overcurrent protection devices is out of the permissible coordination time interval limits. So it may greatly affect the coordination among the protection devices, causing the loss of protection coordination among different overcurrent protection devices in distribution network. So what are the mitigation strategies? So for synchronous based DGs, so the first step is we have to set up the protection setting using the defined standards, and upon the detection of the fault, the algorithm will check this coordination status. If the coordination is lost, so we can restore the lost protection coordination by calculating the sensitive deterioration index, leading to sensitive deterioration ratio, and which is then multiplied with the time delta setting of the relaying devices. And if the relaying devices time dial setting reaches to its maximum limit. So we have to upgrade the size of the link devices. And in the last step, DG capacity is defined for that is suitable for this new protection setting. So for inverter based DG units, we have used the technique like when there is a fault at some point, it leads to the collapse of the voltage. So this collapsing of voltage can be taken as a reference to sense the fault level, and which can be further utilized to define the new reference output generator of the inverter based DG. And in this way, like we can see, we have to define a V set. So when the V reference is greater than this V set value, predefined value, so it will behave as a normal output current conditions. And when during the fault, when V reference is less than this V set value, so it may lead to the fault condition. So upon the detection of the fault condition, it will create a reference signal which will be used to compute the new reference signal for the generation of the output current from the inverter based DG. So it can be used to modify the control pulse width modulation switching mechanism using the state vector modulation. So in this way, we can control the output current of the inverter based DG during the fault conditions. So there are some results that shows the implementation of this the mitigation strategy for inverter based DG. So in figure A, we can see when there is a fault at 0.3 second, three phase fault near the common coupling point. So we can see if there is no mitigation strategy that has been proposed, the output current from the DG units is increased. That may lead to the protection issues. So by using the mitigation strategy, we can see it will calculate the fault level using the reference signal, and this reference signal will be utilized to define the new output current from the DG output. So we can see after about 3 cycles, the output current is reduced according to the new defined signals. So this strategies has been implemented on IEEE 30 bus test system. So we can see in this test system, there are 5 DGs, including 2 inverter based DGs, DG3 and DG5. So the 2 relays, relay R00, that is main breaker relay, and the relay at node 806, R06 has been, the protection coordination among these 2 relays has been investigated. So without the DG integration, we can see these 2 relays were coordinated perfectly with each other. The for a fault at point F1, so we can see the relay R06 provides the primary protection, backup protection provided by the main breaker relay, that is R00. So with the integration of DG, we can see the fault current contribution from the grid side has reduced. It will cause the backup protection that is R00 relay to get out of the permissible CTI limits. So we have to revise the time dial setting of this relay using the proposed algorithm by defining the new sensitive deterioration index and multiplying the sensitive deterioration index with the time dial setting of this relay to get within the permissible CTI limits. So this research work has discussed the protection blindness or the sensitive deterioration of the overcurrent protection devices due to synchronous and inverter-based DG. A quantitative analysis has been performed to assess the protection blindness issues, and a mitigation strategies has been proposed for both synchronous and inverter-based DG, and the mitigation strategies has been implemented and validated on IEEE standardized test systems. Thank you very much.